colleagues get really angry whenever I say that, but it's true. And so I'm going to tell you about some great forecasting failures. You've probably heard of some of these. 2004, there was a magnitude 9 Sumatra earthquake and tsunami, killed about 250,000 people, most of them from the tsunami. And then a few years later, there was a magnitude 9 earthquake in Japan. That killed fewer people, but it has the distinction of being the most costly natural disaster on Earth, primarily because of the tsunami effects on a series of coastal nuclear power plants. So the point of this talk is that we need to do a better job of forecasting these events, in particular not just the big earthquakes, but the ones that tend to produce the big tsunamis. There's one other rather spectacular prediction or forecasting failure. This one, however, was explicitly a project of the USGS and NSF. They spent millions of dollars on this prediction experiment, and it was based on a pretty logical thing. There was a place in Central California where there was an earthquake every 22 years, almost, plus or minus a couple of years. And the last one was in 66, so everybody thought, well, 1988, plus or minus a couple of years. And it should happen again. So let's put a whole bunch of equipment there. And it turns out if you use the models at the time, there was an extremely high probability that the event had to happen before 93. Well, you can guess what happened. After they spent all the money and put all the forecasting equipment there, nothing happened. There was eventually an earthquake in 2004, but it was well outside the prediction window. And so that gave the whole business of earthquake forecasting and earthquake prediction a really bad name. So that's why I decided to get involved. I said, I can do better than that. So I got interested in an area in Costa Rica in Central America called the Nicoya Peninsula. It's an area that sticks out, is close to the trench. And it had a history of magnitude 7.5 earthquakes roughly every 50 years. And so the question is, well, would the next one be in early 2000? And it didn't happen in 2000, and I said, oh, it's got to happen pretty soon. So I started putting equipment out there, and in 2003, we first put 3 CGPS stands for continuous GPS. So instead of taking them back and forth, you just park them there and let them record continuously. And eventually, an earthquake did happen, and by that time, we had something like 13 or 14 of our GPS stations out, as well as a robust seismic network out. So what I want to tell you today is what we learned from that experiment and what we've learned subsequently, and why this shallow water buoy is a great thing to do. So I have to review for you a little bit about what we know about how these big subduction zone earthquakes happen. So here's a cartoon of a subduction zone. So the oceanic lithosphere is diving under the upper plate, usually, sometimes continental lithosphere, and it gets stuck, and so it drags down the or the leading edge of that upper plate with it. And we could measure that motion with GPS. It'll go, areas near the coast will go down and back, and areas a little bit farther inland go up. Eventually, that upper plate gets dragged down so much that it can't deal with it anymore. It breaks the frictional resistance to locking, and it shoots back up, and we call that an earthquake. And since the upper edge of the plate is underwater, it can accelerate a large mass of water, and you get a tsunami. You had a nice talk from Flavio a few weeks ago on this process in a lake. You can get it in an ocean as well, as you all know. And in the earthquake, the reverse happens with the land surfaces. That this part goes down and this part goes up. And then it starts all over again. And so we call those time zones interseismic, coseismic, and post-seismic. So you'll hear me use those terms a few times. So one of the things that seismologists like to do is calculate something called the seismic moment. And moment is just the seismology name for energy. How much energy gets released in an earthquake? And a pretty good rule of thumb for this energy is that it's just related to 3 things. A proportionality constant we'll call mu, geophysicists call it rigidity, and then these 2 things which we can measure, the area of the plate interface that slipped and the displacement, the amount of motion that happened on that area. So you multiply those three things and you get the energy release. And the point is that A and U are both measurable with geodesy. And so in principle, if we could measure A and U before the earthquake, we could tell you something about the size and location of the next earthquake. Now, of course, it's a little more complicated than that. Here's the kind of standard model for this stuff. So it's kind of like a perspective view of that's related to the cartoon I was showing you earlier. We're looking down on the underthrusting plate, the oceanic lithosphere, and we've removed the top plate, the continental lithosphere, or the upper plate. And what you're looking at is our cartoonish view of what that frictional interface between the two plates looks like. And instead of being all locked before the earthquake and then all released after the earthquake, it's a little bit more complicated than that. There's some sort of structure, which we call asperities, to the locking. But we can still measure that. If these are not tiny little things, they're thought to be things of order like oceanic plateaus or seamounts or big things that we can measure and have a measurable impact on the strain pattern of the upper plate where we can put our instruments. So we think we can measure these things to a first approximation. The thing that this slide shows is some terminology that's also important, which we'll call velocity strengthening and velocity weakening. So what the terms mean is that something that's velocity weakening means that the faster it slips, the more that friction gets reduced, and so motion accelerates. So it's an unstable situation. It starts to move a little bit and then it rips. That's what an earthquake does. But there's an alternate type of frictional behavior called velocity strengthening, and that implies some sort of stable state because it starts moving a little bit and the friction increases, so it can't accelerate. And so we think there's these two classes of friction on the plate interface, and we think that the red stuff is velocity weakening, and that's the stuff that goes in the earthquake. Now, if this was always true, then the upper plate, or the uppermost part of the plate, would never accelerate in the earthquake. The earthquake slip would be this lower part, and you'd never get tsunamis. To get a really good tsunami, you have to have this uppermost part of the plate, the upper plate, flip up and accelerate that large mass of water. And there's lots of earthquakes that never do that. They only rupture deeper, don't have any discernible tsunamis with them. And that's the kind of earthquake we have routinely had in Costa Rica for reasons that are not yet clear. So I'm going to make a big deal about that difference later. So the point of this, the next cartoon, is maybe this isn't always true. Maybe these can change over geologic time or through an earthquake cycle, so that sometimes you transition from no tsunami to tsunami. Okay, so here's some, basically based on that introduction, here's some questions we can ask. Why can't we do a better job of forecasting? Can we measure a strain budget, the A and the U part of that equation, and use it to forecast the next earthquake? And then a subtlety related to this is it possible to accumulate strain and store it up so that once there's an earthquake in one place, not all the strain is released, and you might have the next earthquake happen even quicker. We think that this happens sometimes because there's this phenomena called earthquake clustering. They're not as regular as I said they are for Costa Rica. Sometimes they're regular, and then you get a bunch within a few decades. So there must be some sort of mechanism to allow strain to be stored past one earthquake cycle. And then a subtlety embedded in that previous slide is if you get patches like this up here, could we identify them? By definition, they're offshore, and so how could we do that? And that's, of course, where the shallow water buoy is going to come in. Okay, I think I said this, tsunamis imply shallow slip. Do they also require shallow strain accumulation? I think they do. And now I'm going to tell you something about slow slip events. So what is a slow slip event? What is a slow slip? So a slip is like an earthquake. except you can't feel it. So the plate moves, but nobody notices except my instruments. GPS can measure slow slip. I wish I could say that's why I put them there, but that's not true. I only found out about slow slip after the fact. They are actually accompanied by some very subtle types of earthquake-type processes called seismic tremor, but it's subtle enough that the seismologists had never noticed it until about a decade ago. It's a kind of a low-frequency hum that we think accompanies slow slip. Now, why are they important? The reason they're important is that they can, if they're frequent enough and big enough, they can release some of the total accumulated strain so that the earthquake doesn't happen, or an earthquake happens but is not as big as it otherwise would be. So what does it look like? So here's actually some data from a single station in Costa Rica. Each little black dot is a 24-hour average position indicator. I've detrended it, otherwise I have a big slope. And then I fit a red line through that cloud of data. And it's, I think it has an inverse tangent type aspect to it. But anyway, what you can see is that there's some steps in it, but they're not instantaneous. So if there was an earthquake here, it would be an instantaneous drop and then continue on. And what you can see is it's kind of like a smoothed out earthquake. So that's what we mean by slow slip. The time scale here is somewhere between 2 or 3 weeks to 2 or 3 months, typically. The interesting thing, and the thing that convinced me that we were seeing true slow slip events here and not just some sort of noise, is that there's a correlation with seismic tremor. So the blue stuff is the number of minutes of tremor per day, and of course I've chopped off the scale so you can't really read it, but I've kept my own scale, the GPS. So the amount of surface displacement you're seeing is not a huge amount, but we can measure it. So the cool thing is that the tremor seems to mark the beginning of these slow slip events. It's not uniform throughout the slow slip. So we're not sure why that is. Maybe it's just an artifact of limited data, but it is something to keep in mind. The point is, since these are two completely independent data sets, they really confirm that there's something interesting going on here. Okay, so here's a couple of assertions I want to make, and let's see if you can follow them and agree with me. So we're pretty sure that strain accumulation in the interseismic period is a necessary condition for having a big earthquake. It may not be sufficient, but you have to have some strain accumulation. The second thing is that you do need the velocity weakening behavior. Otherwise, it could just be released slowly. And if you have the opposite behavior, the velocity strengthening, that's the sort of thing that we imagine is causing or related to the business of slow slip. So there's, of course, some current dogma about slow slip. The main one is that they occur down dip of the main seismogenic zone. They're deeper than where the earthquake ruptures. Typical earthquake ruptures in a subduction zone are of order 10 to 35 kilometers depth. Most of the slow slip that's been measured in the world is 35 to 45 kilometers depth. I think that's an artifact of where people have been looking, because most of the time you can't see the shallow offshore slow slip. But you'll be able to test my assertion in a few minutes when you look at the data. The other thing that's commonly believed is that slow slip events load the main subduction zone and might bring it closer to an earthquake. And if that's true, it would be a nice way to forecast earthquakes. And we'll see if that's likely to be true or not. So the study area that I'm going to be talking about is here. There's the big scale. Here's this Nicoya Peninsula that sticks out kind of close to the trench. Here's the trench here. Triangles are stations. Yellow is GPS. Is land. What else is happening? Oh yeah, two other important things. So it's pretty fast subduction. So if you went to Cascadia offshore Washington and Oregon, the Juan de Fuca plate comes in at about 4 centimeters a year. This place is coming in pretty fast, 8.5 centimeters a year. So it's really It's on the high end of subduction zone rates. The other interesting thing is that there's actually two types of crust, oceanic crust, that come in here. If you remember you probably don't remember, but there's a spreading center out here. Up here is the East Pacific Rise. Down here is the Cocos-Nazca spreading center. And they produce, respectively, pretty smooth lithosphere and pretty rough lithosphere. So there's a frictional difference in those two lithospheres. And the nucleation point for that 2000 earthquake was right in the middle, right at the boundary. I'm not sure if that's important or it's a coincidence. So something we'll just have to keep working on, I guess. Here's what a typical GPS station looks like. Here's the antenna. It's covered with a plastic radome to keep out the bugs and the snakes. There's a steel box that has two batteries and then the receiver, and then there's a solar panel that keeps it all powered up. Here's some data on the earthquake. The geophysical data is here. There's a magnitude 7.6. There was a total of 4.5 meters of thrust motion on the plate interface. There is a little bit of right lateral motion in the back arc associated with the earthquake. Right lateral just means it's like a San Andreas fault type situation, so that the Costa Rica forearc is actually sliding northwest at a small amount of millimeters per year. And most importantly, there was no tsunami associated with this earthquake. A decade and a half earlier, in '92 in Nicaragua, very similar earthquake, actually a little bit smaller than this, 7.3, had a huge tsunami killing several hundred people. So whether or not a tsunami happens is not necessarily related to the size of the earthquake. There's other stuff going on. Here's some of the geology, which I've mentioned, fast subduction. That EPR and Cocos-Nazca crust is pretty young, under 25 million years. We talked about these things. And interestingly enough, there was no fatalities. Our Costa Rican colleagues who were working with us on that project spent a lot of time educating the public about how to be earthquake safe. And so they were really happy with the outcome of this earthquake. So here's what the GPS data look like from the earthquake. Remember my cartoon of the earthquake? It gets pushed back that way during the interseismic period. And during the coseismic event, it ruptures the other way. So it ruptures this way towards the southwest. So this is the horizontal component of motion. You kind of see the crust flowing in and then flowing away from some central area here. And here's the vertical numbers. I'll show a different view of this in a minute, but basically the coastal area goes up. And what's happening is kind of like this. Here's the overlying plate. Here's the upper surface of the downgoing lithosphere. And there's a section that ruptures. You don't rupture down here and you don't rupture down here. It's just a section about 20, 30, 35 kilometers long. And as it ruptures, crust flows in, flows along, and flows up. And so we can measure these ups and downs. And that's what you're seeing in this plot here. You're seeing the back arc go down and the coastal area go up. It turns out that marks the hinge line for a contrast of behavior. This down dip limit is basically a rheological transition. Above this is what we call brittle behavior. If you're a structural geologist, we talk about the brittle ductile transition. So it's cold and elastic. But below that, it's kind of warm and it also coincides with the moho. So that's about 40 kilometers depth. It's the boundary between continental or arc-type continental crust and oceanic mantle. It's quite wet and quite weak. And so it flows like toothpaste and cannot store seismic strain. If you want to know why it's so weak, you can talk to Jackie. She published a classic paper on this about what happens when olivine gets wet. So now we're looking down again from the top, the satellite view, I guess you could call it. And using that pattern of crustal flow, we can very precisely map what part of the plate interface ruptured. And it's constrained not just by geodesy, but also by a lot of seismic data. So here's that nucleation point where it starts, then it ruptures down and out like that. So that pattern is going to be important. I'm going to refer to that several times. And in particular, I want to show how it relates to the pattern of pre-earthquake strain accumulation. So I'll get to that in a minute. I first have to tell you about how we extract the slow slip events from the data, because the slow slip events are subtle and our data can be quite noisy. GPS tends not to work very well in tropical environments where there's a lot of water vapor in the atmosphere. Water vapor is a big source of noise for us. And we do something called MMSA. I can't even remember what it stands for anymore, but it's related to a principal components analysis. So in that time series of displacements, in those data sets, there's the stuff we want, which is things like the earthquake offset and the slow slip events and the interseismic strain accumulation. And there's a bunch of stuff we don't want: weather-related noise, orbital noise, a few other challenges. And so we separate it into principal components that have both the time aspect and a space aspect, and we throw out the ones we don't want and we keep the ones we do want. And so here's the pre-raw displacement data, and here's the one we like, where we've taken off as much of the noise as we can. And what you can see is we can now identify those slow slip events with a fair degree of reliability. They are the toughest of the Earth processes to extract from the GPS signal. Most of the rest of them are pretty easy. The GPS responds to a number of different processes, but most of them are fairly easy to see and fairly easy to model. So here's an example of that. Here's how we would do this analysis. So the upper rectangle is the data in blue, and then the red is the model that we fit to it. And it includes the slow slip events that we want to extract, but it also includes a number of other things. And you can see that we fit it fairly well. Here is the interseismic component. So basically that's the part where the upper plate is just being pushed back. Here's these slow slip events, these little steps. Here's the 2012 earthquake. That caused a big step in our time series. There's an aftershock, which is another earthquake that occurs after the main one. And then there's a bunch of post-seismic relaxation processes, which I'm not too interested in, but other people are quite interested in. They have several time constants. We model them as exponential decays. They are thought to indicate things like poroelastic rebound, where water gets squeezed out of the upper crust and then flows back in. Earthquake afterslip, which is basically the earthquake slips and then it keeps slipping for the next few months. And then some sort of viscoelastic relaxation in the upper crust, lower crust and upper mantle that can go on for years. So anyway, we can estimate or model all these things and fit our time series pretty accurately. And from that, we can extract the two things I'm interested in, which are the slow slip events and this interseismic locking pattern. If I stack a bunch of these time series together and detrend them, you can see that the slow slip events, which are these blue bars, are happening fairly regularly. These are the ones we think might happen in the future. So I guess I have made a prediction there. So here's what the vectors look like. If you like to think of things in terms of vectors, the slow slip events, remember, are like earthquakes. So they all mean that the Earth's crust is moving to the southwest. So those are happening and mapped as displacements. So over a few weeks, you get a displacement of 1.5 or 2 centimeters or a half centimeter, depending on the distance you are. And then in between the slow slip events, the crust does this interseismic strain, it moves back. And that's a velocity in centimeters per year. So they're opposite, as they should be. So what we're interested in is the slow slip, and then we're also interested in this thing because that's the thing that loads the subduction zone for the earthquake. And so that's the thing we want to map and see how it relates to this. Now, after we get those vectors of displacement or velocity, we have to do some inversions to what's actually happening at depth. I won't go through the details of that. it takes a long time to explain it. But when we're all done, what we get is a nice simple pattern. This is the place, the two places in this piece of real estate that are strongly locked before the earthquake. And these colors is data, and one of these colors is model. I can't remember which is which, but you can see we do a fairly good job of matching the data. The main point is that it's not a uniform pattern of locking. There's basically two patterns of locking. One here under the peninsula and one way over here. If you remember from the earthquake picture, this is the thing that ruptured in the earthquake. Nothing happened over here. So there's a really interesting contrast that we want to understand. The reason for it, I think, relates to slow slip. Because we can go back in time now and look at all the slow slip events that happened before the earthquake. And we can add them up. And when we add them up, we get a pattern that looks like this. So this is that one that was, this is a single slow slip, but here's a bunch of them over a decade-long period, and it repeats. It happens over and over and over again. There's a pattern of seamounts offshore that extend here, so it's possible you're looking at some sort of asperity related to a subducted seamount. Okay, so what's important? Here's where the earthquake happened. Here's my two patterns of accumulated strain. The simple story is that this locked pattern stored up strain, and then it got released in the earthquake. This thing has strain accumulating, but it's being released by slow slip every 2 years. Here's one of these slow slip events. They coincide exactly. So I can show you that in a slightly different way, except I have to get out of this and put on my glasses. And I have to quit PowerPoint. So these slow slip events have a dynamic aspect to them. The pattern of motion migrates along and around the plate interface. So, and we can invert for that. We don't have to treat it as a static thing. We can have it as a time variable thing. So what we've done is we've broken up the plate interface. You're looking down at the plate interface now into these triangles. Here's the data points we have. We have time series at each of those points. And we're going to invert for a time sequence of motion in each of these triangles. Remember that this is where, here's the peninsula, and this is where the earthquake happened. So I want you to kind of stare at that point and watch where the slow slip is happening. Remember, there's some offshore slow slip, and there's some down dip slow slip. All right, let's see if I can get this movie going. So nothing happens at first. It's a nice stable interseismic strain accumulation. Then you start to see a few little things kicking off. Then you get a big patch of slow slip there and a big patch of slow slip here. But my earthquake was here, so you don't get slow slip where the earthquake happens. You get slow slip around the nucleation point of that earthquake. I'll play it once more because it's kind of important. Okay, enough of that.
Was that several months worth of time, approximately?
Yes, exactly. Okay, so now I've plotted the summed slow slip from all the events we captured over a 15-year period. Basically, these two red things. They're contoured in, I think it's millimeters of slip. And then I put on there where the earthquake happened, and it's contoured in millimeters of co-seismic slip. And they don't match exactly. I don't get 300 here, and I don't get anywhere close to 300 offshore. But it's pretty clear that where the earthquake happened, there is no slow slip. So my interpretation of that is that slow slip is relieving the accumulated stress and strain on some patches of the plate interface, but not in others. And so when the earthquake happens, it happens in those areas where strain was not released by slow slip. And I published this in 2014, and it was mostly ignored because people thought it was a one-off, that, yeah, it happens here, but it won't happen anywhere else. So since then, there's been a few other findings that support this sort of connection between slow slip and earthquakes or lack of earthquakes. Here's a paper that came out this year for the Boso Peninsula of central Japan. Slow slip is this stuff here, and it's these are contours of depth on the plate interface. So this is about the same depth that we see offshore Costa Rica for our shallow slow slip. And then the little purple dots are a bunch of smaller earthquakes that have happened in the last X number of years. So here's one indicator that at least one part of Japan has something like this. Here's perhaps a better indicator. In 1944, there was an earthquake on this part of Japan called the Tonankai earthquake. And their rupture area is fairly well constrained because they had good seismic coverage at the time. And then here are a bunch of things called low-frequency earthquakes, which I have not talked about. They're much like seismic tremor. We think that low-frequency earthquakes are more or less a proxy for slow slip. So it's possible that this is a slow slip area, up-dip, shallower than the 44 Tonankai. And then we also have something that just came out in Science Advances, an earthquake sequence in Ecuador. And I'll just read it if you can't read it. These areas, by that they mean slow slip, appear to persistently release stress by aseismic slip, throughout the earthquake cycle, and hence outline the seismic rupture. So there's several places now where this behavior is being observed. Okay, so what does this have to do with tsunamis? Well, remember that slow slip events imply velocity strengthening behavior. The fact that these things occur offshore implies that coseismic slip, for these times we've observed, couldn't propagate offshore, and that limits the potential for tsunami. And then the other implication is if we could measure these things offshore in a reliable way, we could probably do a better job of forecasting. Remember that I was able to get some information offshore because in my Costa Rica experiment, because I had this peninsula that sticks way out. But in most places, we don't have that luxury. We can't see very much offshore. Let me also address one of the things that other people have talked about. Do slow slip events trigger earthquakes? There's been publications based on observations in Japan, Mexico, and Chile that have been interpreted to indicate triggering. We have this kind of stuff in Costa Rica. Here's 3 GPS time series. The earthquake happened here. It kind of, if you look at that, it looks like it triggered, but remember, correlation does not equal causality. And if you calculate something called the Moore-Coulomb failure stress, it implies that the slow slip was insignificant in terms of a stress trigger. You're probably not familiar with Coulomb failure stress. A good example, if I take this pile of paper, is imagine that this is my upper plate, this is the lower plate, and for an earthquake to happen, it has to slide along the table. The ability of this thing to slide along the table depends on 2 things. It depends on how hard I push sideways. Geologists call that the shear stress. It also depends on something called the normal stress. If I'm pushing down hard this way and I push sideways, it doesn't want to move. So this Moore-Coulomb failure stress accounts for both of those types of sideways and vertical stresses. The sideways stress comes from the slow slip event. It means that the upper plate is moving and stressing adjacent parts of the plate. So that's the shear stress. And then the weight of the land mass above the fault plane determines this normal stress. So Coulomb failure stress accounts for both of those things and says, okay, well, how much do you get where the earthquake happened? And it turns out if you do the calculations, you get a very tiny, tiny amount, too small, we think, to have caused the earthquake. So this business of triggering, I'm not convinced, but I could be wrong. I do think, though, it can help us with the forecasting, the business of telling you how big the next earthquake is going to be. Okay, so if it were true, though, that we could use slow slip in this way, we have to worry about what happens when the earthquake happens. Maybe we won't be able to detect them for a long time after a big earthquake. Because remember, an earthquake is a huge meter-level changes in the crust, and I'm trying to measure things that are 5 and 10 millimeters. So how could that work? Raw data, and it implies that it can work pretty well. So the earthquake happened here, and it was meters of motion. And then we start recording every day. And so each dot is a 24-hour position estimate. There was another aftershock earthquake here, so the dots don't act. Here's this post-seismic stuff. But even in the presence of the post-seismic stuff, you can still see these nice little tears in the data. Those are the slow slip events. So we feel that we can capture these things pretty reliably with the current technology. It also appears that when an earthquake happens, it does not affect the timing of these things. So each of these bars is a slow slip event. We've broken them up into deep ones and shallow ones. And the size of the bar is a measure of the seismic moment. Remember, that's the energy, and we can calculate the energy because we know the area of the patch and the amount it moved. And it seems, roughly speaking, that the slow slip events keep marching on at roughly this every 2-year interval, unaffected by the earthquake. I think that's a surprise to a lot of people. So what does that mean in terms of this, what I call a canonical model for subduction zones? I think it means that the subduction zones are not static. That picture of the red patches, it may be true for part of an earthquake cycle, but it's probably not true all the time. You probably have to have some changes. And one way to think about it is the way we think about strike-slip faults like the San Andreas is a pretty simple rheological model. And I'm going to define it for the vertical strike-slip faults, and then I'm going to tilt it over, and that's going to be the model for the subduction zone. So most of the time, you can model what's happening on faults like the San Andreas fault with a really simple model. Upper part, 10 or 15 kilometers, is locked and makes the earthquakes, and below that, everything's just slipping. That's true of probably 90% of strike-slip faults. Every once in a while, it's a little bit more complicated. You get a creeping section. There's a little section in California where the fault creeps and people pave it over or make sidewalks, and you can walk over them, see them offset by a few inches. That's actually not that common. It does happen. So I'm guessing that the same, more or less, is true for subduction zones. Here, I guess my faults got displaced for some reason, but here's the fault, and then these little brackets are just trying to describe the different behaviors. So most of the time, or some of the time, the upper part's locked, the lower part's aseismic. And then some of the time, that upper part is creeping, middle part's locked, and the deeper part is aseismic. So this apparently is a situation we had in Nicoya because slow slip was happening and releasing strain, and so there was no tsunami. And this is probably, or could be, the model for that area to the north in Nicaragua, which caused the big tsunami in 1992. Okay, so how would we go about testing this model? We have to learn more about what's happening offshore in that shallow, slow slip environment. And to do that, we need seafloor geodesy. it's useful to think about two places, the deep stuff and the shallow stuff. So for the deep stuff, one way to do it is with seafloor pressure gauges. And you just measure the vertical component of seafloor motion. If the land moves up, there's less mass of water above it, and so the pressure gauge weighs that. You do need to calibrate for the ocean effects. And then the shallow stuff, I'm going to argue, our buoy that we've been designing here is the way to go. Here's a cartoon of that calibrated deep seafloor pressure gauges. If you had, for example, inverted echo sounders on each of your seafloor pressure gauges, you could measure the speed of sound in water, and that's sensitive to both temperature and salinity, and both of those things affect the density. Okay, what about the shallow water? So it's actually more complicated in shallow water, but there's a lot of places where if we could measure seafloor motion in the shallow environment, it would be really useful. My favorite place is here, Costa Rica, Nicaragua. The red stuff is everything under 200 meters water depth. And so here's the trench along here, and you can see the coastline. So in the northern half of that map, roughly 50% of the real estate between the coastline and the trench is shallower than 200 meters. So that's a lot of real estate that currently we cannot measure in any way. And so that's the environment where I would put these shallow water buoys. This one is Cascadia, about 25 to 30% is under 200 meters. Here's North Island, New Zealand, and here's us, the Gulf of Mexico. Lots of shallow coastal areas. I'd like to do some stuff here looking at subsidence due to the weight of the Mississippi Delta. A lot of other people in the US are especially interested in Cascadia because that's where our big magnitude 9 earthquake and tsunami will likely happen. So there's the detailed 200 meter and less map for Cascadia. Here's the trench somewhere offshore here. Okay, so how are we going to do all this? We're going to build a buoy, and it's going to be, I think of it as like brute force GPS. We're just going to make a big anchor down here. We're going to connect it to a rigid pole. We put a float on the near the surface to keep it buoyant, and above there we have something to hold the GPS. We got this idea by basically reading the literature and seeing what the Italians are doing. The Italians have been doing this for almost a decade around the Gulf of Napoli, where there's a volcano on shore, and they want to measure the deformation of the seafloor associated with that volcano. Their system only measures vertical, and so the way we've augmented it is to put tilt meters on the buoy, and that allows us to solve for the horizontal component. We think this design or something like it will work in water depths up to 150 meters. We've built a much shallower water version of this, and I want to show you some initial results from that. Here's the group of people working. You know these are my colleagues in Geoscience. The buoy looks something like this. Here's Jay Law climbing up to work on the electronics. Solar panels keep it charged. The GPS electronics are here. The very top of the buoy is the GPS antenna. It's the float keeping the whole thing vertical just below the water line. And then here's the concrete ballast that keeps the thing stuck on the seafloor. It's deployed just off Egmont Key. And I can't remember what these are. I think they're other meters, the current or tides. Say again?
Water level.
Oh yeah, thank you. You can read better than I can. So here's what the raw data looks like over 24 hours. Not quite raw, we've processed it. So each dot is a 15-second sample of what the GPS is doing on top of that buoy. And I forgot when we put it in that the outgoing tide is a lot stronger than the incoming tide because you get freshwater input to Tampa Bay. So the tilts to the north west are stronger than the tilts to the southeast. This is roughly vertical in here. So when we crank in our tilt action, it looks something like this. Again, this is a 24-hour average, and that's pretty good performance. We'd like to improve it a little, but I'm pretty happy with it. And then here's the time series up until, I think, early November. I should have updated the slide, but I forgot. So in the GPS world, we always talk about north and east and up. It did a lot of settling early on. We guesstimated that it would spend about 3 months settling and then stop settling. It's actually, I think it's still settling a little bit. It was a surprise to me that there was so much, so negative east means west in the GPS world, so it actually moved west a fair amount by a few meters in the first few weeks, and then it settled down. And the cool thing, I think the cool thing, is that it survived Hurricane Michael. So it did get moved a little bit by the hurricane. There was strong outflowing currents, but no significant damage. Okay, conclusions. Onshore GPS is pretty good at detecting transient events at the few millimeter level, and we've recorded these south slow slip events over the last decade. They've released strength both shallow and deep, and that implies two different types of velocity strengthening behavior. I didn't talk about that too much. Probably not too important for this presentation. And the 2012 earthquake has not changed the frictional behavior, which was a surprise. Here's the main message, I think. Slow slip events limit the size of the subsequent earthquake by reducing the area of strain accumulation. So if you remember one thing from this talk, it's that. And that suggests a motivation for measuring these shallow slow slip events. We need to do a better job of measuring those things offshore, and our shallow water buoy is a start to that process. Okay, there. Thank you.
Thank you. Questions for Tim?
Dave.
What about the timing of this? When would this be deployed in Costa Rica if you were to go there, and where would you deploy it?
Yeah. So I'm actually working on two proposals now. I gave